This video is on piecewise functions. The unit step function, u of t, is defined by u of t is equal to 0 when t is less than 0, and 1 when 0 is less than t. So it just looks like this. From less than 0, it's just equal to 0. And when t is greater than 0, it's equal to 1. By using u of t minus a, you can shift the step function, creating a jump discontinuity at a value other than 0. So for instance, we could translate it so that this discontinuity maybe occurs at t equal to 2. Also, by using m times u of t, you can create a larger or smaller jump. So we could go up here, let's say 4, and this would be 4 times u of t minus 2 if we started here. The rectangular window function, written like so, capital pi sub a b of t, is defined by the unit step function of t minus a minus the unit step function of t minus b. So it's 0 for t is less than a, 1 for when t is between a and b, and 0 for when b is less than t. So it may look like something like this, where it only goes from 1 to 2 and then it stops. Whereas the unit step function, as soon as it starts, it would go on for infinity. Write the function f of t equals 2 when t is between 0 and 3, 4 when t is between 3 and 6, 1 when t is between 6 and 9, and t plus 1 when t is greater than 9, using window and step functions. So this graph is going to be equal to 2 from 0 to 3. Then it's going to be equal to 4 from 3 to 6. Then it's going to be equal to 1 from 6 to 9. And then it's going to be equal to t plus 1 from 9 onward. So that's what the graph's going to look like. Written out algebraically, it's going to look like this. You have 2 times the window function from 0 to 3. So remember, the window function from 0 to 3 would look like this at a height of 1, but we have to double it to get up to 2. Plus 4 times the window function from 3 to 6, plus, oh, I'm sorry, I've misdrawn this because this line isn't all the way up there. It's way down here at 1, because it's 1 between 6 and 9. So we don't have to multiply that window function by anything. That's just pi of 6 to 9, meaning that window function starts at 6 and ends at 9. And then for everything beyond 9, it's t plus 1. So we just draw the line t plus 1 starting there. And it would go on for all values of t greater than 9. So what is the Laplace transform for the unit step function? Well, the Laplacian of u of t minus a is the integral from 0 to infinity of e to the negative st times u of t minus a. But now we need to think of what u of t minus a is. It's just some function that is 0 until you reach a, and then it starts being equal to 1. So it's the same as saying it's the integral of 1, but only over a smaller area, the area being from a to infinity, not from 0 to infinity. So we're going to say that instead of integrating from 0 to infinity, we're only going to start at a, because everything less than a is just 0 anyway. So integrate that, nothing happens, you just get a constant. But if we integrate from a to infinity, well, what are we integrating? U of t minus a is just equal to 1 from a onward. So it's just 1 times e to the negative st. So we're just integrating e to the negative st. We integrate that from a to n as n approaches infinity. We've gone over this many times about how when n equals infinity, this e to the negative nt, that's just going to go to 0. So we're left with positive e to the negative as over s. And that will come in handy. That is our Laplace transform of the unit step function t minus a. Since the window function is capital pi equals u of t minus a minus u of t minus b, and we know that Laplace transforms are linear, we can say that the Laplace transform of the window function is e to the negative as over s minus e to the negative bs over s, as long as a is some value less than b. Okay, we have some identities here. Let f of s, capital F of s, be the Laplacian transform of little f. And let s be some value greater than alpha, where alpha is our value greater than 0. So if a is a positive constant, then we get that the Laplacian of f of t minus a times u of t minus a is just equal to e to the negative as times this Laplacian of f of s. So written alternatively, this is e to the negative as times the Laplacian of f. Conversely, we can kind of do this backwards, where the inverse Laplacian of the right side of that equation is just equal to f of t minus a times u of t minus a. But we also have this perhaps more useful version. The Laplacian of any function of t, it doesn't have to be a function that is already translated by some a. The Laplacian of any function of t multiplied by u of t minus a is equal to e to the negative as times the Laplacian of g of t plus a, where you actually have to shift your g function by a. We're going to see how that works with our next example. Determine the Laplace transform of t squared plus t plus 1 times the unit step function of t minus 1. Well, this is some function g times some unit step t minus a. So we get e to the negative as, but a is just 1. So it's just e to the negative s times the Laplacian of, recall from up here, we have to shift our g function by a. So it becomes g of t plus a, which in this instance is 1. So instead of having t squared plus t plus 1, we get the Laplacian of t plus 1 squared plus t plus 1 plus 1. When you expand that all out, you just get the Laplacian of t squared plus 3t plus 3. And that's equal to, don't forget your e to the negative s on the outside here, but the inside becomes 2 over s cubed plus 3 over s squared plus 3 over s. Okay, we're going to use the same method to determine the Laplace transform of sine t times the unit step function of t plus pi. Well, again, we've got this u of t plus some value a, so that a is going to be multiplied by s in this power. And our g function, our sine of t, it has to be translated by pi. Now, one of our old trig identities is that sine of t plus pi is just negative sine of t. So that'll get us down to this next step. By the linearity of our Laplace transforms, we can take this negative sign and bring it outside. So that's how the negative came outside the brackets. There is a mistake here. I've gone from saying positive pi s to negative pi s. Clearly, only one of those is correct. So let's actually revisit this and figure out which one it should be. we have sine of t times u of t plus pi. Let's go back up to our form. We expect t minus a, but we got t plus a, we got t plus pi. So here, where it should come in as a negative pi, since we have a plus sign here, it's clearly going to come in as a plus pi. So it was correct to put plus pi, so that negative sign should not be there. So we have e to the positive pi s times negative 1 over s squared plus 1. That's our Laplacian of sine t from our table. And then all we do is we bring this negative out front to simplify a little bit, and we finish with negative e to the pi s times 1 over s squared plus 1. Okay, our last example. Determine the inverse Laplace transform of 2e to the negative 4s divided by s cubed, and draw the graph of the solution. So we're going to go back to our identities because one of those spoke about inverse Laplace transforms. This one right here. So if you have something of the form e to the negative as times some function f of s, then that will give you little f of t minus a times u of t minus a as a solution. So let's see what our form is. We do have an e to the negative 4s here. So we know that that is going to come out as u of t minus 4 when you're performing this inverse Laplace. But now we have 2 over s cubed. Well, normally the inverse Laplace of 2 over s cubed is t squared. But let's go back to see what our identity says. You take capital F of s and you don't translate it back to little f of t, you translate it back to little f of t minus a. So inside the bracket, we're going to need to subtract whatever this a value is. Minus 4 means we need to subtract 4 inside the brackets. So it's not t squared, it's t minus 4 squared. So that's how we're reaching this using our identity. But now we've got to actually draw this thing because it says draw the graph of the solution. Well, the unit step function, t minus 4, is going to say we're not going to do anything until we reach a t value of 4. And then normally we would just draw a line at 1 to infinity, and that would be our answer. But we're going to multiply that line by t minus 4 squared. So the graph of t minus 4 squared is actually an upward facing parabola. So that's our solution.